Hello and welcome to Design Considerations. My name is Ed Bray and I will be your host for episode 2 in our battery power series titled Lithium Chemistries. I'm a technical sales and applications engineer with AEM Group located in Raleigh, North Carolina. Today I will be talking with Jeff Nystrom. Jeff is a sales engineer for AEM Group in the Atlanta area. He has been spending a fair amount of time lately working to understand more about various lithium battery chemistries and their prospective applications. Hi, Jeff. Thank you for taking time today to share with us what you have been learning.
My pleasure, Ed. The objective of this discussion is to provide a comprehensive comparison on the pros and cons of the lithium-ion chemistries available on the market, along with other considerations to help you select the best lithium-ion battery for your unique application.
In the brief you shared recently, you described 6 different lithium battery chemistries. The first one was the NCA, or lithium nickel cobalt aluminum oxide. NMC, the lithium nickel manganese cobalt oxide. LCO, or lithium cobalt oxide. LMO, or lithium manganese oxide. LFP, or lithium iron phosphate, and LTO, or lithium titanate. Can you talk about the advantages and disadvantages with each chemistry from an application standpoint?
Sure, Ed. Lithium batteries can either be primary, which is non-rechargeable, or secondary, the rechargeable type. This discussion will focus on secondary batteries, the rechargeable type. Another distinction is a type of lithium battery called lithium polymer, Lipo. Lipo uses non-liquid electrolyte. Typically, it is a gel or a dry material. Lipo commonly uses flexible material for the outer case. They are lightweight and can be made in a variety of shapes, such as very thin or curved. They're used in a wide variety of small portable devices, cell phones, laptops, RC aircraft, etc. They are all custom. This discussion will not include lithium polymer. Instead, it is focused on higher energy, longer life applications, which are dominated by the cylindrical liquid electrolyte type. A good starting point is understanding the difference between specific energy and specific power. For example, a 2-liter bottle holds much more liquid than an 8-ounce coffee cup. The liquid in this case represents energy. The rate of energy discharge is limited by the neck of the bottle. The cup, on the other hand, can be emptied and refilled at a much faster rate than the bottle. This higher rate represents power. Discharge and recharge time, called cycles, is another prime consideration. The different lithium-ion chemistries have a wide variation in the number of cycles. The number of charge-recharge cycles factor into the total cost of ownership. While you do not want to have to replace the battery, you also don't want to pay for a cycle count that outlives the product. In addition to cycle life, all lithium batteries lose total storage capacity over time, which is measured in years. Again, there is a significant variation in calendar year life expectancies. Safety is another big consideration. Some chemistries can literally have a nail driven through them or directly shorted and do not pose any risk of fire or worse. Some chemistries are prone to thermal runaway if they are discharged or recharged improperly, which can result in a fire or explosion, resulting in personal injury, environmental contamination, or other catastrophic consequences. Operating temperature. Lithium batteries, as a group, do not operate well at lower temperature. Some types perform much better in the cold than others. High temperatures can contribute to the thermal runaway, so that is something to keep in mind. The cathode composition is the main difference between the 6 types of chemistries. Most, but not all, contain cobalt in the cathode. Some use iron. Cobalt is a rare metal. Supply has been an issue. Iron and nickel are readily available and inherently safer. Cobalt's electron instability make it a good choice for generating current. It also contributes to its negative characteristics. Overcharging and rapid discharge can lead to high internal temperatures and thermal runaway. Most of the fires you have heard about, like hoverboards and laptops and cell phones and even EVs, are usually caused by this thermal runaway. Nickel, manganese, and other metals are often blended with cobalt to enhance safety and performance. NCA, NMC, NCM, CNM, MNC, and MCN are all cobalt blends with varying levels of safety, longevity, specific energy, and power. Silicon can also be added to the anode to boost battery cell capacity up to 25%. However, the life is significantly reduced due to the fact that silicon expands and contracts during the charge cycles, damaging the container that the battery is in. NCA, which is lithium, nickel, cobalt, aluminum oxide. It has high energy and power density and good cycle count. NCA is a good choice for electric vehicle powertrains. High cost and marginal safety are the negatives. Applications include medical devices, industrial machines, electric powertrains. These are the types of cells mainly used by Panasonic and Tesla. They lend themselves to mass production in high production quantities. NMC, or lithium, nickel, manganese, cobalt oxide, has good overall performance and excels on specific energy. NMC is the preferred candidate for the electric vehicle and has the lowest self-heating. It is a good choice for applications that need frequent cycling, up to 2000, such as automotive and energy storage systems, commonly referred to as EES. Lithium cobalt oxide. It was the original lithium-ion battery. Lithium cobalt excels on high specific energy, but offers only moderate performance in specific power, also in safety and lifespan, typically no more than 500 to 1,000 cycles. Lithium cobalt is losing favor to lithium manganese, especially the NMC and NCA chemistries, because of the high cost of cobalt and improved performance by blending with other active cathode materials. Applications for lithium cobalt oxide include mobile phones, laptops, and cameras. LMO, lithium manganese oxide, has a spinel cathode geometry which gives it high thermal stability and enhanced safety. However, its cycle count and calendar life are limited. Low internal cell resistance enables fast charging and high current discharging. In an 18650 cylindrical package, lithium manganese can be discharged at currents up to 20 to 30 amps with only moderate heat buildup. It is also possible to apply 1-second load pulses of up to 50 amps. Applications include power tools, medical instruments, as well as hybrid and electric vehicles. LFP, lithium iron phosphate. Its key benefits are high current rating, long cycle life, good thermal stability, and enhanced safety. Also tolerance for abuse, such as a direct short or physical damage. LFP has a lower cell voltage than most lithium iron types, 3.2 versus 3.6 volts. However, LFP can deliver higher current and recharge very quickly. Its cost is comparatively high, and its energy to weight ratio is also higher than most lithium ion types. LFP is a good choice for energy storage systems, ESS. LTO, lithium titanate, has advantages over conventional cobalt blended lithium ion. Zero strain properties, no SEI film formation, and no lithium plating when fast charging and charging at low temperature contribute to a very high life cycle, 20,000 cycles or more, and a very good calendar life. Thermal stability under high temperature is also better than other lithium ion systems. It has very good performance at low temperature. Lithium titanate is comparatively expensive, and at only 65 watt-hours per kilogram, the specific energy is low, rivaling that of nickel-cadmium. LTO also charges to 2.8 volts per cell, and the end of discharge is 1.8 per cell. Lithium titanate is one of the safest lithium-ion batteries. Applications include UPS, electric powertrains, Mitsubishi's IMEV and Honda's Fit EV use this battery. Solar-powered street lighting is another application. In closing, consumer applications tend to favor high capacity, while industrial applications tend to favor battery systems with good loading capabilities, long life, and safe, dependable service. We hope this discussion has raised awareness of the many differences in lithium cell construction and will help identify the characteristics that you need from the battery in your specific application.
Thanks, Jeff. Thanks for taking time today to help us understand more about lithium battery chemistries. And thank you for listening. If you would like to be added to our mailing list, would like a copy of the transcript, or have topics that you would like here discussed, go to our website at aemgrp.com and submit under the Contact tab. Next time, we will be discussing wireless design. Until that time, may your designs be safe, robust, and efficient. Goodbye for now.